Okay, cool. Hello, good morning and welcome you to this World River and Delta System Source to Sink webinar series. Today is 21, number 28. And so we invite Dr. Tian Dong from University of Texas at Austin come here talk about the Selenga River Delta in the Lake Baja. Before I introduce Tian, this Wednesday, Anastasia from Los Alamos National Lab, she come here. Will also talk about Arctic river deltas. She will cover at least 6 river deltas over there, including Lena, including the Yukon, Mackenzie, and extra. And also next Friday, Gil Carnegie will come here talk about high concentration suspensions, fluid mart in the river sediment content shelf. I guess we are also including at least the Amazon River systems. So, okay, for example, Anastasia next Wednesday, as I mentioned, she will cover Lena, Yukon, Mackenzie, Yeltsin, all the rivers and the delta systems. And Tian, so as you can see here, he get a master, get a bachelor from UT Austin, and then master and a PhD in Rice University, working with Jeff Neutraver. And now he is an ASF Earth Science postdoc fellow at the UT Austin. So as you can see, he involved a couple with that postdoc fellowship and other couple graduate student grant, and outstanding graduate student award, Rice University, and a couple award, very amazing. So Tian is dedicated working on that, Selenga River Delta, and is a freshwater lake, one of the largest freshwater lake. And it also is a tectonic active region. So this is combined. So I think Tian, now we're looking forward to your talk. So you can share your screen and put a presentation on it.
Okay. Okay, is this good?
Yeah, look, very good.
Okay, all right. Thank you, Paul, for the introduction. And thank you, everyone, for joining on this talk. And very excited to be here today. So here in the background image, I'm showing the Selenga River Delta. This is a delta system that resides on the margin of Lake Baikal, an active rift zone in southern Siberia in Russia. So today in this talk, I would like to share some of the work we have done here in the past several years to explore sediment dispersal dynamics at a tectonically active delta system. So just to motivate this talk to the broader source to sink seminar here, I'm showing an idealized source to sink diagram where sediment and water are generally derived from the headwater region, and they're transported downstream through river systems of different size. And once these rivers enters the receiving basin, typically a delta would form. And I would argue that river deltas are critical parts of the source to sink framework for several reasons. First is that processes occurring in the delta dictates the grain size of sediment that is supplied further downstream to different components of the sink region, such as deep water or coastal systems. And more specifically, over short time scales, hydrodynamics in the delta drives sand deposition locally. So that's sand depositing within the delta itself. And over long time scale, as base level fluctuates, so sea level and subsidence changes, sand is transported into the deep water system. And another important reason for deltas as a critical part of the source to sink framework is that they experience their morphology and stratigraphy are impacted by processes in the source region. So any changes in water and sediment supply, the delta will feel it. More importantly, delta systems worldwide are under stress due to both human and natural causes. So here I'm showing a map of Mississippi Delta in Louisiana. And these red areas are both historical and projected land loss from 1930 to 2050. So these red areas are land that's already lost or will disappear in the next 20 to 30 years. And these land loss actually will reduce the capacity of these coastal communities to buffer against storm surge, hurricane winds, and this can be devastating. So as a resident that live along the Gulf of Mexico, we experience many strong hurricanes that is only predicted to be more frequent in this century. So as an example, here is the Hurricane Katrina in 2005. This is an image of city of New Orleans just the day after Hurricane Katrina, whereby over 80% of the city are inundated. And another event I have lived through personally is Hurricane Harvey that struck and made landfall in Houston in 2017. And this is where I used to live and go to school. So, and this is the photo of the downtown area where a lot of the landscape are inundated. So important part of my research is to understand delta building processes to combat coastal land loss. And one of the ways delta build land in coastal region is through this delta Lobe avulsion process that I will talk about throughout this talk. Here I'm showing an animation of delta Lobe switching of the Mississippi Delta in the Holocene. So over the last 10,000 years or so, the Mississippi Delta is able to build substantial amount of subaerial land in the coastal regions through this process. And this process can arrive just from the internal dynamic of sediment transport and fluid flow in rivers as the river enters a receiving basin. So if we draw a cross section here at the main river, we can see a cartoon of a river cross section with a bankal flow depth of HBF. And the river possesses a mobile alluvial substrate of bed materials. And given the hydrodynamics of the delta system, this alluvial substrate grade over time. And eventually the thickness of the sediment deposit is comparable to the bankful flow depth. And the subsequent flood would drive over bank flow or levee breaching that eventually lead to a selection of new flow path. Hence we call the process of avulsion. So we can constrain the timescale of this process, just use the ratio of bankful flow depths to the vertical aggregation rate of this substrate. And because this process arrives just internally, we typically determine it at the autogenic avulsion timescale. And because river deltas, they experience impacts from both downstream and upstream, the outside controls, where we often term as allogenic impacts, can change this avulsion timescale. So for example, the information coming from the downstream, such as subsidence, sea level changes, and so on, can modify this avulsion timescale. And this is generally information from the sink region. On the other hand, water and sediment supply from the upstream, from the source region, can also impact avulsion timescale and delta morphology. One of the special things about delta is because they experience influence from both upstream, downstream, the source, and the sink region. Over time, delta stratigraphy are excellent record of past climate and tectonic conditions. And one of the pristine sinks that host delta stratigraphy is reef basins due to their high subsidence rate. So here I'm showing an example of delta strata from the two-lake cyclothem in Western Irish Immersion Basin. That's about 310 million years ago. And one of the interesting things in the strata is that a lot of the beddings are deformed by earthquakes, so discrete subsidence events. So how these earthquakes impacts delta stratigraphy or morphology of delta are somewhat understudied. So another aspect of my work is to understand how these discrete subsidence events impact delta morphology and development of stratigraphy. So to address these two themes of my research, I have been working at a system along the active Baikal rift zone. So here is a tectonic map of northeastern Asia, where the Baikal rift zone is roughly in this black box region, where is a divergent boundary between the Siberian craton in the Eurasia plate and the Amurian subplate. And it is thought that this rift initiated about somewhere between 35 to 65 million years ago. And over time, it formed the oldest and the deepest lake in the world, Lake Baikal. Looking closely into the system, here I'm showing the drainage basin of the Selenga Delta, Selenga River. This is the largest water and sediment source that enters Lake Baikal. So majority of the basin is situated in Mongolia, and where we have this high mountain, the Khangai Mountains, sourcing water and sediment. And the river forms the largest Lacustrian delta at the southern shore of Lake Baikal. So in this map, I'm showing the bathymetry of Lake Baikal. Here is the Selenga Delta in this black box, and the delta drains into Lake Baikal, and this lake is the deepest lake in the world. It's about 1,600 meters deep and hosts about almost 25% of liquid fresh water in the world. And because the delta is residing on an active rift system, it experiences earthquakes very frequently. So here is a map of the delta again with different circles, and these circles represent, their size represent earthquake magnitude, ranges from magnitude 3 to magnitude 8. And then some of these earthquakes are quite large and actually very impactful. So in particular, they actually can down drop significant portion of the subaerial delta below mean lake level, about 2 to 3 meters, and forming these embayments that's only 2 to 3 meters deep. And the recurrence interval of these events is roughly about 1,500 years. And the most recent event occurred in 1862, forming Provo Bay, which is this large area highlighted by this red circle. So we can look closely at this event since it's better documented compared to this more ancient events. So here I'm showing a map just of the eastern corner of the delta. Here, these white areas are land, and these gray areas are region impacted by the earthquake. So this map is made by Russian Geography Society just a couple months after the 1862 earthquake. So to highlight some of the features, so in this red line, I'm highlighting the post-earthquake shoreline. And this dashed line is highlighting the pre-earthquake shoreline. So the region between these two shorelines are open water that's created instantaneously overnight. So this is about 200 kilometers squared. That's roughly about 3 meters deep. So this newly created accommodation is formed overnight. And this in combination of the shoreline retreat actually drove a regional shift in water and sediment transport, from the central part of the delta into this eastern part, which is impacted by the earthquake. So since 1862, the delta has prograded into this area rapidly, and this dashed line marks roughly where the modern shoreline is. So the delta has filled in this region both subaerially and subaqueously. Given the rapid geomorphological and tectonic activity, I want to answer some specific questions about this delta. So first, I want to understand how do hydrodynamics in distributary network impact sediment grain size variability, and then how does discrete tectonic subsidence event impact delta Lobe avulsions. And leveraging answer to these questions, I will seek to address some more general some more general questions about deltas. So what are the implications of these findings for development of stratigraphy? And can we develop a practical model to predict flow partitioning in distributary networks? So to address this question, we have conducted field surveys in the Selenga Delta in the past several years. So here's an overview map of the Delta again, where different symbols represent survey transects from different years throughout the Delta. Each location will have collected hydrological and sedimentological data in the modern setting. Just to show you some of the conditions that we lived in the field, here is a panoramic of the field camp where we spent a lot of time in, and then here's some photo of me and collaborators collecting various types of data. After we collect the data, we bring the channel bed sediment sample back to the stage for some grain size analysis. And here are just some examples of the bed material collected from the distributary channel. And as you can see, they are strikingly different. So I will investigate some of these features. So now I'm plotting, in this graph, I'm plotting the bed material grain size in millimeter unit and in log scale as a function of distance downstream camp. And this camp is located near the delta apex at 0, and 40 is the shoreline. And different symbols in this graph are a different percentile of the grain size distribution. So a couple of observations here. One is that grain size finds downstream by nearly 3 orders of magnitude from gravel to fine sand. And another observation is that gravel terminates somewhere in the middle of the delta. So about 20 kilometers or so, there's no more gravel. And another note to make here is that this data is a compilation of several distributary channels. And to look at this data more closely, I'm plotting the gravel termination points for each of the 7 major distributary channels in the delta, showing by these different lines. So the white lines are channels with mixed sand and gravel bed, and then the dark black lines are channels with sand bed. Another observation to make here is that gravel terminates at different locations along different distributary channels. So to understand what is driving this gravel deposition, we first characterize the channel network using channel order. This is just a concept borrowed from tributary systems, where order 1 channel, shown in red line here, is the main stem, and it bifurcates into order 2 channels, into order 3 channels, and so on. And we can look at how channel order varies spatially by plotting channel order and against distance downstream camp. And again, camp is highlighted by the star here. So the observation here is that as we move downstream, the channel has more and more bifurcations. Next, I constrain how hydraulics vary across this distributary channel network based on the field data. So in these 2 plots, I'm plotting bankful water discharge and bankful flow velocity as a function of channel order, so as a function of bifurcation. So as we move downstream, there are more and more bifurcation, and discharge and flow velocity in each branch is decreasing. And not surprising, shear stress, so the sediment transport capacity, also decreases downstream as a function of bifurcation. And now we have an understanding of the transport of the fluid, transport capacity of the fluid, we compare it to the sediment grain size itself. So here, to evaluate the transport capacity of the flow, we use a simple framework, the gravel transport stage, which is just a ratio of the boundary shear stress, which is force of the river flow, to the critical shear stress, which is force required to initiate gravel motion. And to highlight that, we use the smallest D90 the critical stress rate of the smallest D90 to represent, to use in this framework. This is because this D90 is the smallest gravel in the upstream region, but the coarsest in the downstream region. So it represents the full spatial variability of the gravel. And now we will calculate this parameter everywhere in our survey transact in the delta. And if this parameter is greater than or equal to 1, the channel has the capacity to transport gravel. If it's less than 1, no gravel is transported. So here is a map showing the predicted gravel transport stage for each survey location indicated by the circles. So the white circle is T greater than 1, so gravel transport. And black circles are T less than 1, so no gravel transport. And after we make a prediction, we can compare it to our observation, which is showing by these lines, which I showed earlier. So white lines are mixed sand and gravel bed, which coincide with our predicted gravel transport stage. And the black lines are sandbed channel, which coincide with our predicted sand transport stage. So this takes us to our first question: how do hydrodynamics in distributary channel impact sediment grain size? What we find is that channel bed sediment size finds downstream from gravel to sand in the Selenga Delta. And this is driven by a reduction in sediment transport capacity due to flow partitioning in the distributary network. So in the source to sink framework, this could imply that over a short time scale, hydrodynamics in distributary channel could reduce supply sediment to other systems downstream of the delta. One of the good part of working in Siberia is we experience great nature and culture at Baikal. So this region have very rich culture from the Breyas people, and they also have very unique ecosystem. So this is the Baikal seal. It's a very cute animal, and they are evolutionarily independent from ocean seals. Now, as I mentioned earlier in the introduction slide, this frequently occurring impact for earthquakes would trigger regional scale shift in flow of water and sediment, which essentially is a Lobe scale delta avulsion. So here I'm showing an overview map of the delta again, where on land I'm showing elevation, and in the lake I'm showing the bathymetry of the lake. And this dashed black line is the 40-meter isobath, just highlighting the shallow water region just surrounding the delta itself. The shallow region are highly impacted by this subsidence events. And this dark line here is the 1862 shoreline. And just to know that this green DM background is made in mid-2000. So the delta has filled in this area in the past 150 years or so. So from historical data, we know these tectonic driven avulsions occurs every 1500 years or so. So we term this as the tectonic timescale, which is driving autogenic, so externally created avulsions. So we want to compare this to the internal dynamic of the river delta system to the autogenic avulsion timescale. So just driven by the transport of water and sediment, as I also mentioned in the introduction slide. So, and this internal avulsion timescale can be approximated using delta slope, radius, and the water depth around the delta. So I conducted a remote sensing survey to constrain these parameters. So first I have set up a survey grid, a semicircular survey grid along the delta, where I set up a survey transect from the delta apex, and the transect moves along the semicircle. So I have used about 180 transects, so they're spaced about 1 degree along this semicircle. So along this arc, I will measure shoreline positions. So these different color lines are shoreline of the delta compiled from both historical maps and Landsat images from 1862 to 2019. So we can measure the shoreline progradation rate and radius of the delta. And we can now take a look at this data. So here, this map, I'm showing radius of the delta in the y-axis against time, moving forward to the right. And this is for the eastern part of the delta, which is the area that's impacted by the earthquake. So the gray dots are the entire raw data, and then the circles are decadal averages. So in general, the long-term trend is that the shoreline is prograding at about 26 meters per year in the eastern part of the delta. And on the other hand, for the middle part of the delta, where water and sediment has been diverted to this region, is actually experiencing retreat. So this is the central part of the delta. Similar plot and axes. And what we observe is that shoreline is actually retreating over time due to both compaction and probably due to both compaction and a reduction in water and sediment due to this regional shift in flow. So from this, we have constrained the radius of the delta. Next, we can explore the surface, the slope of the delta. Here I'm plotting the elevation of the delta surface, plot against distance downstream of delta apex again. And these gray lines are all the data, and then the dashed line here is the average slope. So surface slope of the delta is about 3.28 times 10 to the negative 4. So the last parameter we need to constrain is the water depth of delta. So here is a map I showed earlier where I have highlighted the embayments around the delta, where our colleagues in Irkutsk have collected the water depth data along this delta, which I'm showing here. So here are two histograms of water depths in these two embayments. They're roughly about 2 to 3 meters. So now with our parameters constrained for this autogenic avulsion timescale, by also considering uncertainties in these variables, we can calculate a probability distribution of the autogenic delta Lobe avulsion timescale shown here. So the median value is about 9,200 years, plus minus the first and third quantile. And we can compare this to the tectonic driven autogenic avulsion timescale. So again, here is a map I showed earlier, which is highlighting the shift in flow direction due to the earthquake. And this tectonic driven timescale is about 1,500 years. And then compared to our theoretically derived autogenic timescale, which is 9,200 years, this internal autogenic avulsion timescale is much longer than the autogenic avulsion timescale. And this indicates that this discrete subsidence events predominantly triggers delta Lobe avulsions. So which brings us to the second question of this talk. On active margins, delta Lobe avulsion could be predominantly triggered by discrete tectonic subsidence events. And the implication is that allogenic forcing predominantly controls Lobe switching process for deltas on active margins. And moving forward, I want to explore how addressing these two questions, so the hydrodynamics and subsidence, what are their implications on stratigraphy? So one of the first implication is that because these events are discrete, they essentially time blocks a part of the delta topset and recorded in the stratigraphy. Here is a legacy seismic survey conducted by USGS and Russian Academy of Science collaboration in the early 90s. So this line shot just in front of the delta. So here I'm showing the seismic line here. The y-axis are both depth and two-way travel times. And here I'm showing some of the interpreted stratas by previous authors. And their interpretations is that what we see is we have this linear, very continuous stratus, they interpreted this as pro-delta suspension foul, and with they overlay these clinoforms, which the authors interpreted as shallow water delta topset deposits, but now they exist in water depths that's about 600 meters deep. So my take, given our new understanding of the surface processing on the subaerial land part of the delta, I would interpret these as discrete packages that's downdropped by different earthquake events. So I have highlighted about 5 of them. So within each package, there's distributary deposits and various channel forms. Another implication of the surface processing is that the dynamics of the gravel front. So here I'm showing a schematic of the current configuration of the gravel front in the Selenga Delta. So the dark brown part is the gravel bed channels. And because there is a continuous inflow of gravel, the front of the gravel must prograde downstream, as indicated here. And if we draw a cross section, a 1D dipped section here, what we see is that in order for the gravel to prograde downstream, the newly coming in gravel need to grade the channel bed slope to a higher gradient to overcome the sediment transport capacity reduction driven by the bifurcations. So we can estimate the timescale required to build this new volume. I'll give it this simple trapezoidal geometry. First, we can constrain the gravel inflow using our hydraulic and sedimentological measurement, combining with this mixed sand and gravel transport equation developed by Wilcox and Crow. And then we can use this calculated sediment flux, related that to the amount of gravel required to grade to this new gradient. And that takes about 1,700 years. Meanwhile, we know that earthquakes occurs in the delta, they're constantly creating new accommodation. As I mentioned throughout this talk, this tectonic timescale is about 1,500 years. So these two timescales are very similar. So this implies that it's very difficult for the gravel to prograde downstream because you're creating accommodation at a faster rate than the infilling rate. An implication of this arrested gravel front is that coarse material is trapped on the subaerial delta, and only mud is transferred to the basin. So another implication is the preferential preservation of mud in the basin. And to test this hypothesis or implication, we look at the legacy work by the USGS and RAS collaboration again. So they collected some cores in the delta front, and this course ranges between 1 to 5 meters. And this dark color just indicate mud. So at least for the last 35,000 years or so, most of the delta front are filled with mud. So the gravel really hasn't moved for a significant amount of time. So to bring this all together to our third question is that the implication of the surface process is that first, gravel is trapped on the subaerial delta and only mud is transferred to the basin. So tectonic subsidence could impact grain size on the subaerial delta and in the basin. Another implication is that subsidence events could be preserved as discrete stratus. So which implies that interpretation of Deltaic stratigraphy on active margin should be aware of these discontinuous surfaces bounding the discrete stratus that represent different earthquake events. So doing a lot of this field work required helpers in the field. So I have met a lot of interesting people and animals around the Selenga Delta. And especially we'll have this friendly dog that guards our sediment samples. So one of the problems I encountered doing field work out here is that it's very difficult to collect water and sediment discharge information in the Delta network. And because field location is somewhat remote and the channel network is spatially extensive. So really, there's a need for a practical method to predict flow partitioning. So as mentioned, most large Delta systems with a complex channel network, the gauging station is normally in the main stem of the Delta or in the main river that's several tens of hundreds of kilometers upstream of the channel network. So we really don't know what is going on inside of the distributary channel. And collecting flow information everywhere in the Delta is very costly and time consuming. And modeling efforts are typically focused on single bifurcation, so really resolving the flow field in single bifurcation, or for network scale flow simulations, you really need detailed bathymetric map of the channel bed to start that, which is hard to collect in the first place. So to get around it, a recently developed method is that it uses a graph to approximate flow partitioning in the river delta. So to explain, this method actually couples hydraulics at individual bifurcations to the topology of the network. So this is done through a routed directed acyclic graph. To explain this very quickly, here I'm showing a simple graph with 4 nodes, 1, 2, 3, 4. They are connected by 4 edges, indicated by the lines. Routed graph means all information originates from node 1 and passes down to the daughter nodes. Directed means there's a direction of which information travels, as indicated by the arrow. And acyclic means that whichever information travels downstream doesn't come back to the root node. So this is very, very useful. We can approximate flow in river deltas. So here I'm showing a very simple schematic of a distributary network. We can apply the same rule here, which we connect bifurcations and confluence using the nodes and vertices. And to represent the flow and the connection between different bifurcation nodes, mathematically, we rely on the adjacency matrix. To explain this, we know there's a flow and a connection between bifurcation 1 and 2. So here what we see is a non-zero entry in column 1, row 2. So the non-zero entry in the adjacency matrix represent a connection between bifurcations, and the row and column number represent the downstream and upstream, so the flow direction. Furthermore, we can represent the strength of the connection using the weighted adjacency matrix. So essentially, this is highlighting the flow partitioning at the bifurcation. For example, here we have 0.2 in row 2, column 1. This indicates 20% of flow is traveling down this branch, where in row 3, column 1, there is number 0.8, so that indicates 80% of flow is traveling down this branch. So typically a nodal relation is used to approximate flow division at individual bifurcations. For example, here a particular flux Q1 is coming down the main stem of the delta, is split into Q2 and Q3. Typically this is approximated using ratio of the channel width highlighted by B here. So using this framework. And I have tested a range of remotely sensed hydraulic variables to see which relation is actually the most useful and most predictive. I have come to the conclusion that a combination of width and sinuosity of the downstream branch are a very good remotely sensed variables to predict flow partitioning. And I have tested this against field data collected from the Selenga Delta. So here I'm plotting predicted discharge of the downstream branch using these 2 parameters against measured discharge for water, as well as for total sediment discharge. So these are this relation are in pretty good agreement with field data. So now I can apply this to a graph model. First, I have digitized the Selenga distributed channel into a graph where these gray areas are vertices and the red highlights the outlets of the delta. And again, the goal is to construct adjacency matrix so we can predict flow throughout the network. And I have constructed about 142 by 142 matrix. Finally, this leads us to our prediction. So here I'm showing a predicted flow partitioning in the delta, showing the skeleton of the channel network. And this different color lines is indicating this parameter called F, which is just a ratio of the discharge in individual branch divided by the mainstream discharge. So for example, the purple lines are the less thick, the thick line here I'm highlighting it. There are branches that partition about 20 to 50% of the main flow, where the gray line here, there are branches partition about 5% of the total inflow. So if we add everything up at the shoreline, it will equal to 1 versus the same at the input. And these different circles are our survey transects that where we have collected flow information to validate this model. So let's compare the prediction to our measurements. So here I'm showing model predicted water discharge on the x-axis against measured water discharge at various field locations. Generally, the model did pretty good. We can do this similarly for total sediment discharge in a similar plot configuration. The model did a decent job at predicting total sediment discharge as well. Another advantage of this model is that it can also predict time series data, given a time series of input at the upstream. So here I will look at the predicted hydrograph for this particular location in the delta, so this red circle here. So here I'm showing a hydrograph of at this location where discharge is shown at the y-axis and time on the x-axis. So the solid line here is our field measured hydrograph, and the dashed line here is our graph model predicted hydrograph. And we can do it's a similar exercise for total sediment discharge. The uncertainty is a little bigger, but overall, the model does a decent job at predicting total sediment discharge as well, time series of total sediment discharge. To further test this model, I have applied it to some other delta systems. First is the Lena River Delta, also in Russia. Here is a similar predictive flow partitioning with similar color schemes. We can compare it to some literature data of water discharge at these gauging stations. So here again, I'm plotting predicted versus measured water discharge. In general, these two values are in good agreement. I've also tested this in another system, the Wax Lake Delta in Louisiana here in the States, using some of the data collected by Matt Hyatt in 2013. Again, similar plot configuration, by which we find good agreement between model prediction and field measurement as well. So this leads to the last part of our talk, where can we develop a practical model to predict flow partitioning in distributary networks? The short answer is yes. And more importantly, this model is really practical and quite easy to apply. And so, it provides a first order prediction for large scale delta. First order prediction of flow partitioning, for large delta systems that's difficult to access or where field data might be limited. And to conclude and summarize of this entire talk, I'm bringing back to the overall source to sink framework of this seminar. So again, I'm showing the idealized source to sink diagram again. Based on the research we have conducted at the Selenga Delta, we have learned that on active margins, tectonic subsidence can impact delta lobe switching processes and stratigraphy stratigraphic development at the delta. In addition, subsidence, tectonic subsidence alongside of delta hydrodynamics actually can severely impact sediment grain size that is supplied to different parts of the downstream components of the overall sink region. For example, beach and barrier island systems in the coastal area and the deep water systems such as submarine canyons. And finally, we have developed a practical model that actually can predict flow partitioning in delta networks under given various input of water and sediment supply, which is predicted to change under the changing climate in the source region. So with this, I'll conclude my talk by acknowledging my collaborators in the field throughout the year and the funding agencies. I'd also like to thank my family for the support during my absence in the field, especially my wife. So with that, I will open to questions. Thank you for listening.
Thank you, Tian, for this great talk. I mean, that's such a great tectonic active, and it's the last earthquake is only about less than 200 years, right? So
yes.
So that's great. Okay. I say Jim, go ahead. I know maybe you have to go in 15 minutes. So you go ahead. Yeah, Jim. Let me sorry. Okay, now you can unmute yourself.
I thought you were trying to mute me on purpose, Paul.
No.
John, thanks ever so much. As always, really good talk, fascinating as well. I apologize if you addressed this earlier, I might have missed it. But in terms of looking at sort of the controls on avulsion, does lake level change play any part over, the Holocene or a period of, 100,000 years? Because, how has that varied, and what magnitude of variation might that be compared to, say, I don't know, the displacement due to tectonics? Any ideas?
Yeah, so based on what I read through the literatures, lake level is roughly more or less somewhat constant on the 100,000 years timescale, because although glacial cycle varies through those time, but because the high latitude location is somewhat, the evaporation is somewhat not very time variable.
Go ahead. Sorry.
It should be on the meter scale, and then today in the modern setting, the lake is currently dammed, so the outflow channel is dammed. So there's an annual fluctuation is about around 1 meter.
Okay. Okay.
Yeah.
So throughout the last couple hundred thousand years, it's going to be really small compared to any tectonic displacement.
Yeah, and also I guess these tectonic influences are highly localized, and they directly impact the delta compared to the overall lake level shift that could be spatially variable as well, given the large scale of the lake.
Okay. Okay.
Yeah,
thanks ever so much. It was really good, fascinating talk.
Yeah, thank you, Jim.
So, Tian, quick question. I guess the tide, the water level fluctuation over there is almost minimum, right?
Yeah, yeah. So based on what I again from literature, it's about like 0.3 meters, so 30.
Oh, 30, some kind of millimeter. Okay.
30 centimeter. Yeah,
30 scale. Yeah, 30 centimeter. Yeah.
But it's worse for us to constrain though. To go out there and find out.
Okay, very good. Okay, Gil, go ahead.
Hi, Tian. It's really good to see you, and that was a great talk. That's the first time that I've seen your PhD work, and so thanks. It was really great. And so I was interested in the last part of your talk and the sort of the method to try to estimate water and sediment discharge. And so with I guess I just wonder if you could say a little bit more about how you kind of deal with grain size and bed load versus suspended load, or is it like you're starting from downstream of the gravel fronts? Or are you considering everything is going to be suspended load, and do you have, you know, some percentage of mud versus sand? Or I guess I just wonder if you could comment a little bit how grain size figures into this, or not.
Okay. Yeah, I guess the short answer is that the model doesn't really have a capacity to model grain size, and it actually doesn't do very well to predict bed load transport, you know, just because there's a lot of local variability in bed load transport. So and this is also not what the model intended to do in the place to resolve like bed load transport. It just to give a first order approximation of, you know, where are the largest channels just from, you know, remote sensing image, where are the regional flow scale, and if you give some perturbations, does that changes the regional flow? And you know, I am trying to think about some future work to kind of improve the prediction of this framework to, you know, to better predict bed load, because, you know, there's a lot of local deposition and erosion that this model doesn't really capture, because at the end of the day it's not a morphodynamic model. Yeah.
Oh, I totally agree. Bed load is really is a challenge.
Yeah, it's hard.
But I guess when you were reporting like your QS, your sediment discharge in like a meters cube per second, is that the units you're using? And so it's just like a bulk suspended load, bulk suspended load discharge that's predicting, I take it.
Yeah, it's so I guess to address that, so the Selenga is pretty typical of the lowland river. So majority of the load is suspended load. So like bed load is only about 5%, like the time average bed load. So the model predicts suspended load pretty well because, you know, it's related to water, it quickly reaches steady state. So and then it does total load really well because, you know, majority part of that is suspended load. So, but when you look at bed load individually, it's not that good. It's not that great, which I didn't really show.
Great, thanks.
Okay, anybody else? Michael.
You know, I'm wondering that you're seeing that the tectonics are driving a lot of the avulsions, and then you're prograding out packages of sediments. You know, what's the average thicknesses of these packages as they move around?
Yeah, that's a great question, and this is something we want to explore in the future. And right now we only have one example, the most recent event, which is our average is about 3 meters, so the average distributary channel depth. And literature has also reported the maximum subsidence is about 9 meters, and the minimum is about 1 meter. So anywhere between 1 to 9 meters would be, you know, the variability in these packages, and their spatial area would be, you know, a couple hundred, you know, 1 to 200 kilometers squared.
Right.
So I guess with new technology, you know, you could resolve that, the internal structures, I would say. Paul would know more.
Interesting. So, Tian, another quick question. Is there any dominant longshore current in the near the river mouth?
Yeah, I think, let me go find a picture of the delta. Yes, this is something, here. So these barrier islands.
This is from left to right?
Yeah, from left to right. So from like south to the north, roughly.
Oh.
So these are poorly understood how they move, you know, how they protect where these sediments was supplying these islands, or how they change, you know. So this is something you know, definitely the part of the future work. Yeah. So yeah, basically, you know, water depths behind the barrier, you know, between the delta and the barrier island are very shallow, and then, you you know, once you go out in this open lake, you know,
Oh.
it's the water depth pretty quickly, you know, drops to about, you know, a couple hundred meters.
Oh, so the sediment dispersal, I guess here, even we have a longshore current, but still dominately by the cross shelf, just to go directly to the deep part.
Yeah, I don't have the image here, but I can show you some literature that actually there's a submarine canyon actually leads all the way up to right about here. It's pretty fantastic. So, you know, I think a lot of people in the audience are, you know, interested in that, you know.
Sure. Definitely we need more work like what we did of a little bit underwater, right, Gil?
Yeah.
So that's very good. That's very interesting. Okay, anybody else? Oh, by the way, do you have a rough estimate how much sediment from the surrounding river dumped to the lake and how much they flew out? Because this is part of the upper reach of the Yeltsin River, right?
Oh, yeah, actually, I don't know. Oh, you mean how much sediment is entering Lake Baikal and what's the percentage that are leaving the lake?
Yeah, yeah.
I don't know. I don't think
any part leaving.
Yeah, I don't think there's maybe some suspended part might leaving like really fine stuff because I think there's a ramp for the outflow channel.
Oh.
The outflow channel is only, you know, is situated way on top of the
like a dam. Okay.
Yeah.
Okay. Interesting. Cool. Very nice. Very, very nice.
Yeah, thank you. Thank you for having me.
Okay. Okay, anybody else? If not, you know, I think, you know, thank you, Tian. This is the great work. Hopefully, you know, in the next couple of years, we can extend the work a little bit to the underwater portion. Okay.
Yes.
Let's have a little bit talk with Jeff to see what we can do, you know. And I
Okay.
really want to bring my chip. Okay, cool. Thank you very much.
Thank you.
And
thank
Gil,
you.
you will stay here a couple of minutes for you know, test your Zoom. Okay. Then rest of the weekend. Okay.